In this tutorial, you will learn how to drive and dim COB LEDs using a 12-bit timer and lookup table. In the description below the video, you will find a link to a GitHub repository that includes a wiring schematic, the bill of materials, and detailed explanations for each line of code. So let's have a look at a bit of theory regarding how LEDs are driven, dimming, flicker, and pulse width modulation. Unlike resistors, capacitors or inductors, LEDs are nonlinear electronic devices. A small change in voltage results in an exponential change in current. That's why LEDs must be driven at their rated voltage and current, and the current must remain constant at all times. Without a current-limiting resistor or driver, an LED gets warm, its resistance declines, and more current will flow, and this cycle repeats until the LED is destroyed. This effect is known as thermal runaway. It is possible to use a resistor to limit the current, but that means wasting a lot of energy. The proper solution is an LED driver that keeps the current constant at all times, a device that also steps the input voltage up or down to the LED's rated voltage. It may sound a bit confusing at first, but linear dimming appears nonlinear, while nonlinear dimming appears linear. In other words, because of human brightness perception, we have to dim nonlinear, so the change in illumination appears linear. Simple COB LED drivers generate perceptible flicker, even if we don't seem to notice it. And flicker is also visible at certain shutter speeds and frame rates when using a camera. Human-centric lighting should reduce flicker to a minimum. To dim COB LEDs, we use pulse width modulation, which means rapidly switching the LED on and off with an oscillating square wave to control the mean voltage. The dimming level is controlled by the mean voltage, and so we change the duty cycle per period. For visually correct dimming and flicker reduction, we need to apply pulse width modulation in a specific way. The higher we raise the frequency, the number of pulses per second, the perceptible flicker is reduced. Human brightness perception follows a curve described by the negative quadrant of a COB LED function. We can use this function to generate pulse width modulation values so that the voltage change is nonlinear, but the brightness perception change is linear. Linear dimming with 8-bit pulse width modulation values appears nonlinear. Therefore, we'll use values on the COB LED curve, and instead of complex floating point runtime calculations, we store and retrieve precomputed values from a lookup table. The benefit of using 12-bit resolution is that it provides us with 4096 values instead of only 255 with a standard 8 bits. The larger range allows us to distribute the pulse width modulation values much better. To keep it simple, we keep hardware to a minimum, because the clever stuff happens as always in the code. Here's an overview of all parts in case you're not so familiar with them. You'll need the specified components, but you can find cheaper substitutes online. The wiring of the setup is really straightforward. And now a quick demonstration. As expected, slow automatic dimming looks linear and smooth, thanks to the timer and lookup table based approach to pulse width modulation. It doesn't matter how the dimming is triggered, automatically with a potentiometer, a momentary or proximity switch. Like I mentioned in the beginning, the clever stuff happens always in the code. Every line of code is carefully commented so you can learn the logic step by step. So please head over to GitHub and take a good look. Once you understood the approach taken here, you can confidently code dimming features for your own luminaire designs. And now it is your turn. Thank you for watching and listening.